Hello everybody. We start today's lecture and I would like to begin with recall. Recall what we proved last time. So A Lebesgue is Lebesgue measurable. Then we could represent it as follows. The intersection of union AI trace without A naught, where AIJs are elementary and AI1 is included into so on. And if we denote BI is union of AIJs, then B1 includes B2 and so on. That is what we have proved. Yeah, and also measure of B1 is finite, and also here we supposed measure of A is finite, and measure of A naught is 0. That is structure of Lebesgue measurable sets. And if we look at this assertion, so for elementary sets, so what is elementary set? It's something like that in R2, finite union of intervals. Part of the boundary is included, part of the boundary is not included, and if we will consider interior, then interior is again an elementary set, and you see that volume of the elementary set coincides with the volume of the interior. So it means that in fact we can consider, instead of elementary sets, the interiors, and as a corollary, so corollary of that assertion, I can formulate the following property. So if A is Lebesgue measurable, and measure is finite, then we can represent it either as a countable intersection of open sets without, okay, let's say P naught, where GI are open and measure of P naught is 0, or also we can represent as a union of closed sets together with, let's say, Q naught, where Fi are closed, and again measure of Q naught is 0. The second representation follows by taking complements. Okay, And now I would like to make a remark. So for arbitrary bounded set A, its outer Lebesgue measure can be represented as infimum of measures of G, where we take infimum over all open sets which contain A, and inner Lebesgue measure analogously can be represented as supremum of measures of closed sets which are included into our A. So also it follows from that theorem, or from that corollary, in other words. And you see that yeah, it can be compared with another remark where I gave you an alternative description of Jordan measurable set. So elementary, and analogously inner Jordan measure is supremum of, yeah, here I could take volume, because these are elementary sets which are included, once again elementary. So you see, that is another way to define Lebesgue and Jordan measures of sets in Rn, and you see also quite similar, but for Jordan measure we take elementary sets, and for Lebesgue measure we take either open or closed sets, and that is another way to define Lebesgue measure, in fact. Okay, so now let me give useful criterion, theorem 9, criterion of Jordan measurability. A bounded set A, once again let me recall that we consider subsets of Rn. A bounded set A is Jordan measurable if and only if Jordan measure of the boundary equals to 0. That is very useful criterion, and in fact, if you compare, for example, with Zorich textbook, that is practically a definition of Zorich doesn't define Jordan measurability, but instead of that he considers other equivalent notion I don't want to mention, but in fact you can find this as a definition of this equivalent notion. And So let us prove. I'll start with necessity part. So we suppose A is Jordan measurable. Then, by the remark which I mentioned, they exist elementary sets E1, E2, elementary, such that U1 is a subset of A and A is a subset of A2, and I forget to insert for arbitrary epsilon greater than 0, of course. For arbitrary epsilon greater than 0, such that volume of the difference is less than epsilon. And also, as I mentioned, volume of the interior equals to volume of U1, because interior means we delete boundary. Of course, volume doesn't change. And volume of closure equals to volume of E2 analogously, because closure means that we add the whole boundary to the set. Of course, volume doesn't change once again. And the relation, of these inclusions will take place for interior and closure respectively. So in the following, we can suppose E1 is open, E2 is closed. Okay. Now let me recall what is the boundary. The boundary, one of possible characterizations of the boundary is closure without interior. Hence, we can observe the following thing. So, if I'll consider outer Jordan measure of the boundary, then, since this is closed, that is another property of the boundary which was mentioned before, that is closed set, and if it is closed, then outer Jordan measure coincides with Lebesgue measure. There was a corollary in one of former lectures. So for closed sets, outer Jordan measure coincides with Lebesgue measure. Then Lebesgue measure of the difference, because both are Lebesgue measurable, open and closed sets are Lebesgue measurable, so we can write measure of a bar minus measure of the interior. And yeah, also, in fact, I don't need it. Sorry, I don't need it. In fact, we can proceed easier. I don't need it. So, boundary, look, we know that closure is an E2 because we supposed E2 is closed. And interior contains E1 because we supposed E1 is open. Hence, if we consider the difference, then it is a subset of E2 minus E1. So the boundary is a subset of this set. Hence, measure of the boundary is less or equal than measure of E2 minus E1, which is just the volume because that is elementary set. And by the construction, recall, this volume was less than epsilon. So what do we have? We have now that for arbitrary epsilon greater than 0, outer Jordan measure of the boundary is less than epsilon. Hence, this outer Jordan measure is equal to 0. And of course, then it coincides with Jordan measure because inner measure is less or equal and all of them are non-negative always. Hence, necessity part is proved. Now, sufficiency. 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 So now we suppose that Jordan measure, of the boundary is 0. Then let me estimate. Yeah, I have to use some properties of inner and outer Jordan measures here. Okay, let's start with outer Jordan measure of our set A. That is less or equal than outer Jordan measure of the closure. A bar is closure. I used both closure. Yeah, not good. A bar. Okay, let it be A bar. So there are two notations. Let me recall. Closure is also denoted like that. That is what I use here. Okay, this is closed. Hence, by what I mentioned in the proof of necessity part, it coincides with measure, Lebesgue measure of the closure. And now I have to use this equality that is equal to measure of the interior plus measure of the boundary. and we know that Jordan measure of the boundary is 0, hence Lebesgue measure is also 0, because if a set is Jordan measurable, then it is Lebesgue measurable. So we obtain measure of the interior of A, and interior of A is open set, and for open sets, Lebesgue measure coincides with inner Jordan measure of interior. So for open sets, Lebesgue measure coincides with inner Jordan measure, and inner Jordan measure of the interior is less or equal than inner Jordan measure of the sets itself, because interior is a subset of A. And what we have? Yeah, and finally, of course, inner measure of arbitrary set is less or equal than outer measure. So you see that we started with a number and we finished with the same number. Hence, we have equality everywhere here. And what means equality here? Equality here means that the set A is Jordan measurable. And that is what we wanted to prove. And theorem is proved. Theorem is proved. Okay, now I would like to consider a couple of examples, and a very important example. Let me give it here. Example 1. Counter set. That is rather famous set. Also, it is called counter-ternary set. So, what is it? Consider I naught equals to 0, 1. Such an interval, and I'll denote it by I naught. So, let me draw a picture to show what is going on. So we have the interval 0, 1. Let us divide it in 3 equal parts. And so divide it into 3 equal intervals. And delete the middle open interval. Okay, let it be J1 equals to 1/3, 2/3. So what it means? It means that we consider I1 to be I naught minus J1, and that is I11 together with I12. So we have a union of 2 closed intervals, 0, 1/3 and 2/3, 1. These are two equal intervals. Now divide each of I1, I. At the moment we have only two such intervals, right? Into three equal parts and repeat the construction. So it means now I take 1/3, 2/3, and here 6, 7, 9, 8/9, and so I delete that interval. Now I delete those middle parts. So it means that now I consider I2, that is by definition I1 minus J2, where J2 is now union of two middles, right? So J21 together with J22, that is interval 1/9, 2/9, together with 7/9, 8/9. Yeah, and also I2 now consists of four intervals: I21, I22, I23, I24, and we repeat that construction. So next time we divide each of those four intervals into three equal pieces and delete middle part. So by definition, the counter set P is the intersection of what remains. Okay, let us think what we obtain. What are properties of this counter set? So first of all, what we have as an intersection? I can observe that what is it? That is I naught without the union of all intervals which were deleted. So we deleted a lot of intervals. So each of JJ's, recall, that is a union of some intervals, and we delete them. So, and from each of those representations, you see these are closed, and arbitrary intersection of closed sets is again closed. or from here, union of open sets is open, complement of open is closed. So counter set is closed. Closed set. Closed set. Of course, it is not empty because obviously ends of intervals are included into P, right? But surprisingly, that is uncountable set. So let us prove P is uncountable. That is, the best way to see it is to use ternary fraction. Ternary fraction. Let us represent by ternary fractions numbers in our counter set. So look, how we may characterize, for example, J1. J1. J1 consists of all real numbers which have the ternary fraction representation 0.1 and so on. That is ternary fraction, right? I hope you know what means ternary fraction. So that is 0 plus 1/3 plus something, right? What is less than 1/3? Less than 1/3. Analogously, what is about J2? J2, or maybe J21, for example. J21, analogously, they have the representation 0.01 and then so on. J22, they have the representation 0.21 and then other digits. Digits are 0, 1, and 2. No more digits in ternary fractions. Yeah. So then what remains? So you see, it means that yeah, by the way, 1/3 can be represented without 1 like 0.0222222. That is like in decimals, decimal fractions with period of 9. And of course, 2/3 also can be represented without 1, right? So that gives a characterization of P. So P consists of all real numbers which have the ternary fraction representation without digit 1. So yeah, of all real numbers in 0, 1, in 0, 1, of course, in 0, 1, in 0, 1. Yeah. And then what it means, let me now explain why it proves that P is uncountable. Recall that my claim is that P is uncountable set. So look, P consists of ternary fractions of the following form, something like 2, 0, 2, 2, 0, 2, and so on, right? These are ternary fractions which form together the whole counter set, right? And then we can put one-to-one correspondence. So now put the following, the one-to-one correspondence between P and the binary fractions. This correspondence is as follows. So I can give it by an example. So what we do? We replace every 2 by 1. And now it will be binary fraction. So look, we have ternary fractions without 1. So only digits 0 and 2, nothing else. Now we replace every digit 2 by 1. We obtain now a fraction of this form, and we consider it as a binary fraction now. That is the one-to-one correspondence, right? Obviously. But what is about those binary fractions? Obviously, every real number has a representation as a binary fraction. So it means that we have one-to-one correspondence between P and the interval 0, 1, and in fact even more. I mean, you see, the set of all such binary fractions, it contains more than 0, 1, because, for example, 1/2 can be represented as 0.1000 binary fraction, also like 0.011 and so on binary fraction, right? These are two binary fractions which corresponded to different ternary fractions. That is that one, and that is 0.022, so on, ternary fraction. Yeah, in fact, that is 1/3. I gave somewhere, yeah, here I gave, and that is 2/3, right? So those two numbers have the same image in binary fractions. So it means that we have correspondence between P and the set which contains 0, 1 as a subset. So it means that in fact our P is indeed uncountable. It has continuum cardinality, the set of continuum cardinality. Now let us compute the measure of Cantor's set. So, yeah, in fact, it's easier to compute Lebesgue measure, because for the Lebesgue measure, since we, by construction, we have all sets J's are disjoint, then we can write measure of I naught without sum of measures JJ's, and JJ, they contain finitely many intervals, so everywhere we can write volumes in R1 lengths. And that is 1 minus, okay, what do we have here? Measure or volume of J1 is 1/3. We deleted firstly the middle 1/3. Measure of J2 is 2 times 1/9. That is 1/3 times 2/3. Measure of J3, we'll need to consider 8 intervals. So 8 intervals. Each of them will have the length 1/27. And that is once again 1/3 times, oh, why 8? 4 intervals. 4 intervals. Yeah. 1. Yeah. Next time we had 4 intervals. 1/27. So 1/3 times 2/3 squared. And it's easy to understand that every time we'll need to multiply by 2/3. So we have this expression 1/3 times 2/3 power j, and we can compute it. 1 minus 1/3 times 2/3, 1 minus 2/3. Is it correct? 1/3. 2 times 1/9, yeah, and 4 times 1/27, 2/3, j. Oh, sorry, j minus 1. No, j minus 1 here. Yeah, j minus 1. So, yeah, then we start with 1 here. Yeah. Then we have 0. Then we have 0. Then we have 0. And since P is closed set, that is precisely outer Jordan measure. And if outer Jordan measure is 0, then the inner Jordan measure is also 0, and it is Jordan measure. So you see that counter set has Jordan measure 0. But it's clear that we can modify a little bit. So if we take J1 of the length, let's say alpha 1, J2, two intervals of the length, total length alpha 2, and so on, then we have measure of such modified counter set. So I repeat the construction, but every time we delete smaller intervals of total lengths alpha 1, alpha 2, and so on, then as a result measure will be 1 minus sum of alpha j's. And if we have this series with sum smaller than 1, right, then we can obtain positive measure here, and once again it will be the same as outer Jordan measure of P tilde, which is positive now, but for the inner Jordan measure of arbitrary such sets, doesn't matter how many you delete. You see that by construction, look at the picture. Every time we delete something in every of those parts, now not necessarily 2 over 3, 7 over 9, 8 over 9, now different numbers are here, right? But every time we delete middle part in each of those intervals. Middle parts, they have now larger lengths, but doesn't matter. So every time we delete something, so it means that we cannot find an interval inside our set, our modified counter set. So it means that no elementary set is inside, hence inner measure is always, inner Jordan measure is always 0. So if we modify counter set by this condition, then we obtain closed set which is not Jordan measurable. In fact, I saw one textbook where there is a problem to prove that counter set is not Jordan measurable, what is not true, as I said. But also I have to apologize that in my lecture notes, which are in Russian on the site of our department, there is also a mistake where I gave an example of alphas, which gives in fact 0 here, but I asserted not 0. That was a mistake. So there are mistakes with that set quite often. Okay, next example. Now I want to give an example. So here I gave to you an example of non-trivial Jordan non-measurable set. We had one more example of rational numbers. Rational numbers also form non-measurable Jordan in Jordan sense. But now an example of Lebesgue non-measurable set. So once again, consider 0, 1. 0, 1. And let us introduce introduce an equivalence relation. So two numbers x, y are equivalent if x minus y is rational. It's easy to check that this is indeed an equivalence relation between numbers. Hence, we have classes of equivalence. Hence, 0, 1 can be represented as the union of classes. So these are classes of equivalence. Classes of equivalence. Okay. Now, maybe minus 1, 1 I should start. No, 0, 1, 0, 1. Now, form a set E by choosing precisely one element from each class alpha. Yeah. Yeah. Now, I would like to use the property of Lebesgue measure that it is shift invariant. But firstly, let us enumerate all rational numbers from minus 1, 1. So I from 1 to infinity, that is precisely rational numbers from minus 1, 1. And put EI by definition, that is the set of X which are represented by X equals to Y plus Ri, where Y varies in the set E. So it means that we shift each of sets E to the rational Ri. So EI are shifted sets E. Okay, I want to claim that these are disjoint. These sets are disjoint. Why? By contradiction. if EI intersected with EJ contains a point Z, let's say, right? Then what it means? And I not equals to J. I not equals to J. What it means? It means that there exists, let's say, X in EI such that Z equals to X plus Ri, and there exists Y in EJ such that Z equals to Y plus Xj. No, sorry, Rj. Yeah. So X in E, sorry, X and E such that Z equals to X plus Ri, yeah, and Y in E such that Z equals to Y plus Rj. Then look what we obtain. It follows from those two that if we subtract, then we obtain X minus Y equals to 0 equals to X minus Y plus Ri minus Rj, Rj minus Ri. That is a rational number. And it means that, of course, X is not equal to Y, right? Because Ri and Rj are different. And now what we have? We have two elements of E which are equivalent, right? Two elements of E which are equivalent because their difference is rational. It means that X and Y should be in one class. But remember, E was constructed by choosing precisely one element from one class. So we cannot have two elements from one class in our E. That's impossible. That is contradiction, right? So it means that these are disjoint sets. And then very simple consequence. So suppose now E is Lebesgue measure. Then measure of each of EI's equals to measure of E for all I, because, as I said, Lebesgue measure is shift invariant. And now, look. For every X in 0, 1, right, there is Y in E such that X minus Y is rational. Why? Because, remember, 0, 1 was represented as a union of classes, right? Hence, X belongs to sum of classes. And for sure, we have a represent of that class in our E, and for each, so x and y are in one class, hence the difference is rational, right? And okay, then what is about this rational? Both x and y are in 0, 1, so the difference belongs to minus 1, 1, right? Hence, x minus y equals to ri. And it means that x belongs to ei for some number I. So there exists I such that x belongs to ei. And what it means? It means that union, disjoint union of all sets ej contains 0, 1. And measure of this disjoint union which is by definition, not by definition, by sigma additivity of Lebesgue measure, sum of measures, and each of measures coincides with mu e, is greater or equal than measure of the interval 0, 1, which is 1. So it means that it follows that measure of E should be positive. It cannot be 0. Otherwise, we have sum of zeros. From the other side, look, every ej, how it is formed? We took an element from 0, 1, and we added rational number from minus 1 to 1. So every ei is a subset of minus 1, 2. Hence, the union is also a subset of minus 1, 2. Hence, we have similar inequality, but now that is less or equal than measure of minus 1, 2, which is 3. And look, if we have here positive number, then sum of this series is infinity. And that is a contradiction. So it proves that our set E is not Lebesgue measurable. And in fact, you see that the construction is very strange. I mean, we use very non-clear procedure. I mean, how to choose precisely one element from each of uncountably many sets. That is very strange procedure. And in fact, there are no examples of Lebesgue non-measurable sets which are constructed without this procedure, very strange procedure. So most of sets which appear in applications are Lebesgue measurable, in fact. Okay, now I finished this very long section. Of course, I don't plan to ask you a lot from that section, but something I will choose, but very few assertions, of course. Definitely example of non-measurable is rather complicated, but Cantor set will be included for sure. Yeah. Okay, now next section, and that is section 6, if I remember correctly. Section 6, geometric applications. Geometric applications of Riemann integral revisited. And now I'll start with theorem 1 here. So if f is Riemann integrable on AB, Riemann integrable, and f of x greater or equal to 0 for all x in AB, then the subgraph the set of x, y such that a less or equal x less or equal to b and 0 less or equal to y less or equal to f of x is Jordan measurable. And Jordan measure of this subgraph, how to denote it? Let's say T. Subgraph, let it be T. And Jordan measure of T is equal to the integral f of x dx. Proof. We know that the integral is simultaneously lower and upper Darboux integral, so that is supremum of all lower Darboux sums and infimum of all upper Darboux sums. So P are partitions of our interval, and lower Darboux sum is where mj is infimum f of x for the interval xj minus 1 xj, and delta xj is the length of this interval xj minus 1. And analogously for upper Darboux sum is that one, where mj is supremum. For all x in the same interval of f of x. So let me draw the picture. X, y, a, b. So we have our subgraph. It's here, that one. Y equals to f of x. We have a partition. And so lower Darboux sum, if you look to what is it, then we recognize that the lower Darboux sum is the area of this union of rectangles. And this union of rectangles is an elementary set. That is elementary set E1. So E1 is the elementary set such that its volume, two-dimensional volume means area, equals to the lower Darboux sum for this partition. That is x1, x2, so on, right? So it means that in the Darboux measure of our subgraph, which is by remark I mentioned it today. So in the Jordan measure equals to supremum for all elementary sets in T of volumes of T, right? Hence, we see that this is greater or equal than supremum for all partitions of lower Darboux sums. Because, look, here we should consider all elementary sets which are included in our subgraph, and every lower Darboux sum is the volume of such an elementary set, right? Okay. Analogously, for upper Darboux measure, that is infimum for all elementary sets which contain T, and once again this infimum is less or equal than infimum for all P of U of Pf. And you see, we know these are equal. Hence, since we always have inequality in the measure is less or equal than outer, so we have because of that chain, in fact, we have equality here. We have equality here, and and it means that Jordan measure coincides with the integral, what we wanted to prove. So you see, one of the reasons why I preferred to give the elements of Jordan measure was here, because that is very important application of the integral. So the integral is the area, because Jordan measure for the plane is area. And but we need to know what is area. And Jordan measure theory, that is precisely the theory of area and volumes in R2 and R3 respectively. So theorem is proved, and one example. Let us compute area of a disk. And okay, let it be unit disk. Oh, it doesn't matter, let it be arbitrary, right? So consider y equals to square root of r squared minus x squared minus r less or equal s less or equal to r, right? It means that we have such a curve, right? And according to our theorem, the Jordan measure of this t is semi-disk, in fact, right, is equal to the integral from minus r to r of our function. And we can compute this integral easily. So substitute x equals to sine t, then dx cosine t dt, and yeah, if x equals to minus r, r will be included also, minus r, then t equals to minus pi over 2, and x equals to r corresponds to t equals to pi over 2. So we have integral from minus pi over 2 up to pi over 2 cosine r squared cosine squared t dt. Cosine squared, that is 1/2 of from minus pi over 2 to pi over 2, 1 plus cosine 2t over 2 dt. That gives r squared times t over 2 plus 1/4 sine 2t, substitution from minus pi over 2 to pi over 2. And it gives finally, yeah, the result is, as we should know from the elementary geometry, pi r squared over 2. And it gives the area of the whole disk 2 times this number, so pi r squared. That means that now the formula for the area of a disk is proved, finally. Of course, you know this formula from the school, but in the school it was not proved because there was not rigorous theory of area. Now the theory of area was constructed completely, so it means that the formula for the area of a disk is proved rigorously. Yeah, okay. And it seems I have no time. I plan to give one more application today for the volume, but I think it's better to continue next time. Okay, that's all for today. Thanks for your attention. And why no questions? Very strange. Very strange. No questions. Okay, thanks for your attention anyway, and bye-bye.